All right, so we're going to be talking in this chapter about building and learning how to graph linear and quadratic functions. So we're going to start off with linear functions and their properties, and then building linear models. So we're mostly going to be focused on this portion, which is the linear models portion. Okay, so the first thing we need to talk about is what the linear function looks like. Okay, so a linear function is a function of the form f of x equals mx plus b, where again, m is just slope and b represents slope, and b represents the y-intercept. Okay, so in other words, this is where it crosses through the y-axis. So just kind of looking at this without using the example, if I were to graph f of x equals mx plus b, it would look something like this, where I'd have a point B that it goes through, and it would go in one direction with a straight line, okay? And we'll talk more about that in this example here. All right, so we've got a function. It says we want to graph the linear function f of x equals negative 3x plus 7, and then we're going to discuss what the domain and the range of this function is. Okay, so to start off, let's go ahead and graph it. So we have a y-intercept of positive 7. So I'm going to go ahead and put a point here at positive 7. Okay, and something that we could do, if you're not familiar with slope, is we could simply plug a few points in and see what we get out. Okay, so we've got x, f of x. I'm just going to do a couple points to the right of this. We know that this is going to be a straight line. We'll do 1 and 2. We'll stop at that, right? So I've got negative 3 times 1, so negative 3 times 1 plus 7, and that gives us, let's see, that'd be negative 3 plus 7 would be 4. Okay, we do the same thing with the next one, so this would be negative 3 times 2, which is negative 6, plus 7 is 1. Okay, and so I can just plot these 2 points. So it's going to be to the right 1 and up 4, so right there. And then we have to the right 2 and up 1 right there. And we can draw our as straight of a line as we can, remembering that we can still keep picking points to the left and to the right of this. So we need to make sure that we're putting arrows here. All right, so now we can take a look at this graph, and we can figure out what the domain and range is, right? So remember, to indicate that we're talking about domain, make sure you at least put that D there. Okay, and same thing with the range. If we're looking at the range, remember that you need to at least indicate that you're talking about the range by putting an R. Okay, so domain is talking about how far to the left and how far to the right, or what the inputs that we can pick for X are. Okay, so what we're looking for are the arrows. So if we're looking at the far left, so the furthest thing to the left, notice that we have an arrow here. So we're going to start this with an arrow. Okay, and we don't have any holes, but on the far right, we also have an arrow. Okay, and because we don't have any holes, we can actually connect the 2 dots, which this tells us that if we have an arrow to the left, that means that it's going to start at negative infinity. If we have an arrow to the right, it's going to start at positive infinity. And because there's no holes, it's going to be a continuous line. Okay, so this is the domain of our function. All right, range is the same thing. So we're going to look at the top. Notice that we have an arrow at the top. We look at the bottom. Notice there's an arrow at the bottom. And then we're going to look to see if there's any gaps in our line. In this case, there are no gaps. So we can simply connect our line. Okay, so we know that it's going to start at negative infinity. Remember, it always starts at the bottom. Then it goes up to positive infinity. All right, and that's all I'm looking for there. Okay, so what if I were to ask you, let's talk about average rate of change to identify linear functions. So we're going to look at the same function, okay? But in order to be a linear function, that means that it has to have a continuous rate of change. Okay, so in other words, the difference between one point to the next has to be the exact same. All right, so let's kind of look at what this means. All right, so let's go ahead, and all we're doing here is we're going to plug in negative 2 into our function. So I have f of negative 2, is equal to, that'd be -3 times -2 plus 7. Calculating that gives us, what is it, 13? Okay, then we're going to calculate the next one, same process. So f of -1 would give us 10. Okay, and I'm going to calculate the difference. Let's go ahead and do all these real quick. So f of 0 would be 7, f of 1 would be 4, f of 2 is 1, and f of 3 is -2. Okay, so now what we're going to do is we're going to take a look and see what the difference between my y values are. So notice that on my x values, we're just adding 1 in each step. Okay, so the increments are not changing. We're not making this. We're not increasing by 1, then 2, then 3, or decreasing by the same amount. So we're keeping the rate the same, okay? So let's take a look at this one. And again, to be linear, they have to have the same rate of change, okay? So from 13 to 10, it's -3. From 10 to 7, it's -3. 7 to 4, it's -3, -3, and -3. Okay, so we have a rate of change of -3. And notice that this actually corresponds with our slope. Okay, and so our slope is actually, and we already know this, but our slope is our rate of change. Okay, so we can state that this is a linear function. All right, so let's go ahead and kind of define something. It says a linear function has a constant rate of change. That is, the average rate of change of a linear function f of x equals mx plus b is delta y over delta x. So what that says, what this is actually saying, is it's a change in x, or sorry, in y, divided by the change in x, okay? Or y1, or sorry, y2 minus y1 divided by x2 minus x1. Okay, and again, these are things that we've talked about. Now, I want to go ahead and prove this. Okay, so what we're going to do is we're going to prove this this figure. All right, so that's what we're going to do in this next part. In order to prove, so it says the average rate of change of f of x equals mx plus b from x1 to x2, where they're not equal, where x1 and x2 are not equal to each other. And you'll see why that is here in just a minute, and we're going to prove this. So we're going to say, we're claiming that delta y over delta x is equal to our slope, okay? So the first thing we're going to do is we're going to talk about this in terms of what it means, okay? So we know that delta y, well, we know that our y's are actually f of x, right? So y equals f of x. So I'm going to go ahead and rewrite this in terms of f of x. Okay, so I've got f of x2 minus f of x1, right? So this would be the change in y's, okay, over the change in x's. So I started with f of x2, so I need to start with x2 minus x1. Okay, then we're going to go ahead and when we know that f of x is equal to mx plus b, so we can replace this, right? So we have m times x2 plus b minus m times x2 plus b, sorry, that'd be x1 plus b. We can't replace anything on bottom, so it's still going to be x2 minus x1. All right, so now we can kind of look at it and kind of break this down into its parts. So let's go ahead and actually distribute this negative into the parentheses and get rid of these parentheses. So we have m x2 plus b on the front minus m x1 minus b. Okay, you'll notice that these b's are the same terms. We can actually subtract them out. Okay, and what we're left with is mx2 minus mx1 on top. Okay, So we're going to use that fact, and I'm going to look and see, well, what do we have in common here? Okay, notice that both of these have a coefficient of m. Okay, so I'm going to factor that out. Okay, so I've got m times, so that's our common factor, and then we're going to rewrite our remaining factors and what's left over. So we've got x2 minus x1 divided by x2 minus x1. Okay, and remember, we can divide something out if we have the same factor on top as we do on bottom. Notice that here I have x2 minus x1 on top. I have an x2 minus x1 on bottom. So I can actually divide those out. Those divide to 1, and all I'm left with is our slope. So in this, we have just proven that the change in y over the change in x is equal to our slope, or equal to m. Okay, so let's go ahead and move on. It says a strain of E. coli, E. coli Bu 397, is placed in a petri dish at 30 degrees and allowed to grow. The data in the table below are collected. What population is the population is measured in grams and time in hours. Plot the ordered pair xy in the Cartesian plane. So the Cartesian plane is just an xy plane. And use the average rate of change to determine whether the function is linear. All right, so let's go ahead and start by determining whether this is linear, right? So we can actually determine that by checking the interval. So we can say this is a difference of +1, this is +1, +1, +1, and +1. Okay, so our intervals are the same. All right, what about the y's? So checking the y's, this is plus 0.3, plus 0.4, 0.04, sorry, this is 0.03 and 0.04, 0.03, 0.04, and already we have a different rate of change, so we know that this is not linear. Okay, but if we were to actually graph this, we can also tell that it's not linear. So when we're graphing these, we're going to kind of identify the x and y. So x is going to represent the number of hours. So I'm going to go ahead and label this as hours. And y is the population. And we could put in grams if you want. All right, now we need to start labeling this. So hours, we can go up by an increment of 1. Okay, so my hours is going to go from 0 right here to 1, 2, 3, 4, 5. My y values, though, need to go up by decimals, right? So in this case, I'm actually going to go up by 0.1s. Okay, so we'll say 0.1, 0.2, 0.3, 0.4. Okay, and then we're just going to graph. Okay, so I've got my points right here, so I'm just going to graph these points. So 0 is 0.09 would be somewhere right in here. Okay, this is just going to be kind of an estimate to see where we're at. 1.12, so somewhere right in here. 2.16, so closer to the middle between those two. 3.22, so right up here. 4.29, so really close to 3. And then 5.39, so somewhere really close to where 4 is. So if we were to trace this line, notice that it kind of curves upward. Okay, so it has an upward trend to our data set. All right, so again, this is not linear, both by graphing it. So if we were to graph it and if we were to just kind of look at the intervals, we could tell that it's not, that we can't use it. All right, So this time, again, we could go ahead and we could just kind of count and check, right? And I'll show you guys how to do these in your calculator when we're in class on the next time. So I'll show you how to type these into the calculator and kind of get an estimate of what these look like. But I'm going to go ahead and claim that based off of this information, that this is linear. Okay, but I want to go ahead and focus in on actually graphing this, right? So I'm going to take a look and I'm going to say the x-axis represents the age and the y-axis represents the heartbeats. Okay. All right. So let's go ahead and plot these. So notice that my x-axis is going up by 10. So I'm just going to go ahead and simply go up by 10s here. So we've got 10, 20, 30, 40, and I think it goes up to 50. Let's make sure. Oh, nope, it goes up to 70. So 60 and 70. Okay, so those are my x-axis. Now we need to look at the heartbeat. So the heartbeat, you'll notice, they start at 37.5 and they go up to 50. So what I'm going to do, this is called a graph break. Okay, so we have this little break to say that we're skipping a whole lot of numbers. And now I'm just going to go up by 5. So I'm going to start at 35, then I'm going to go to 40, then I'll go to 45, then to 50, and the maximum heart rate that we had was 50, so we can actually stop there. And in fact, I can space these out just a little bit better. So 35, 40, 45, and we'll go to 50 here. All right, so let's graph these. Okay, plotting these points, we have at age of 20, the maximum heartbeat is 50, so right up here. Then we have at age of 30, it's 47.5, so right in between 45 and 50. At 40, we have a maximum heart rate of 45. Then at 50, we have a maximum heart rate of 42.5, and then 60 is 40, and then 70 is 37.5. Okay, and here we do have a linear relation because we have this straight line, so we could continue to go downward. All right. So this is a linear function. This is how you're going to tell, either by counting or you can simply graph it. All right. So the next thing I'm going to ask you to do is to determine whether these linear functions are increasing, decreasing, or constant. And the way you can do this is by simply looking at the number in front of the x and determining whether it's positive or negative. If it is positive, it is increasing. Okay? If it is negative, it is decreasing. Okay? So using that information, go ahead and pause the video now and really quickly do this. Okay? And you should have got that this was increasing. Okay? Again, we tell that by whether it's positive or negative. Our slope is positive or negative. Okay? Now this last one, notice that we don't have a variable. Okay? All we have is our constant. So because all we're left with is our constant, this is actually going to be constant, right? This is a horizontal line that goes through y equals 7. All right. So we're going to go through some linear modeling. Okay, so to model a linear function, we need to know what the slope is, or the rate of change, and we need to know where this would be the starting point. Okay. So with mathematical models, typically, you're not going to be dealing with anything outside of the first quadrant. So remember, quadrants are 1, 2, 3, and 4. The reason most of our area is going to be in the first quadrant is going to be because we're looking at profits and real-world situations where the input has to be, where the input has to be positive and the output needs to be positive. Okay, so that's typically what we're going to be looking at, but there will be some instances where that may not be true. Okay, so it says if the average rate of change of a function is constant, is a constant slope, right? So we talked about linear functions. A linear function can be used to model the relationship between the two variables. Okay, again, the two variables are f and x. Okay, those are the two variables that they're talking about here. And they can be we can use this function here where b is the value f at 0, and that is f of 0. So in other words, we're plugging in f of x. All right. So in example 2, we're talking about book value. So book value is how much a company believes something is worth, one of their assets are worth. So book value is the value of an asset at a company. A book value is the value of an asset that the company uses to create its balance sheet. Some companies depreciate their assets using straight line depreciation so that the asset declines by a fixed amount each year. The amount of decline depends on the useful life that the company places on the asset. Suppose that a company just purchased a fleet of new cars for its sales force at a cost of $28,000 per car. The company chooses to depreciate each vehicle using a straight line method over 7 years. This means that each car will depreciate by $28,000 over 7, which they just kind of gave it to you, $4,000 per year. Step A, they're asking us to build a linear model that expresses the book value V of each car as a function of its age, x. Okay, so we have two variables here, right? So we've talked about this. Okay, it's really important to be able to indicate the model that we're expressing. So we're looking at book value, so we're using V as a function of x. Okay, so what we need to pull from this this problem is the initial value. Right, so we need to pull the initial value, and we need to be able to pull the slope, okay, or the change in the value. Okay, so we can start with the initial value. So the initial value is actually going to be $28,000 per car, okay, because we bought the cars for $28,000. And then it's going to depreciate. So depreciate means it's going to lessen in value by an average of $4,000 per year, okay, and that's going to be our slope. Okay, so using this information, we can actually build a model. So we have 4,000 times x, okay, so times the age of the car, plus 28,000. Okay, now one thing you do need to remember is that this is a depreciation value. Okay, so when it depreciates, it's going to subtract. Okay, so our model should be negative 4,000x, or negative 4,000 times the age of the car, plus 28,000. All right, part B says, what is the implied domain of the function found in part A? Okay, so remember, the domain is what we're plugging in. Okay, so we're looking at what we're plugging in to determine what the domain is. Okay, so in knowing this, x represents the age of the car. Okay, so if the age of the car, we can't have a negative age, so we're going to start our domain at 0. Okay, and when we first buy them, it is 0 years old. Okay, and then we're going to end our domain at where we would probably sell the car. Now, we're going to go ahead and start the domain at positive infinity. Okay, so we could have a car that's 20 years old, but more than likely at 20 years old, that car is going to be costing the company more money than it's actually worth. And we'll adjust this domain here in just a second as we go through this. All right, so graph the linear function. Okay, and I do want you guys to actually start practicing on graphing this. So I'm going to go ahead and over here. Actually, I've got a graph down here. So we're going to use this graph down here. Okay, and we know that it starts at 28,000. Okay, so remember that this is our initial starting point, And our domain, we're saying, goes from 0 to infinity. So what we're actually looking for here is where it's going to cross the x-axis. Okay, so we've got 28,000, so this is cost, book value. We'll call this book value. So value. And this is age. Okay. So we want to know where it crosses through the x-axis. It actually ends up being right at 8 years. Okay, and we'll talk about that here in just a little bit. Actually, sorry, it crosses here at 7 years. Okay, and we'll talk about where that came from here in just a little bit. But we can draw our line through these two values. Okay, so we have a book value that's going down through the ages. So we've got 1, 2, 3, 4, 5, 6, and 7. All right. So part D. Part D is saying what is the book value of each car after 3 years. Okay, so that is our age. So what I'm going to do is I'm simply going to say what is the V of 3. You can type this into your calculator here. Okay, so it'd be negative 4,000 times 3 minus plus 28,000, and you actually get a book value of $16,000 after 3 years. And that would be, if we were to graph it, put it on our graph, that would be this point right here. So this would be the point 3 comma 16,000. Okay. Part E is asking for us to interpret the slope. Okay, all that's doing is saying, what does this mean? Okay, so all we need to say is that the book value decreases by $4,000 per year. Okay, so I'm just asking you to write in words what they're already telling us. All right, and then finally, it's saying when will the book value of each car cost $8,000? Okay, so when does the book value? Okay, so we're looking for the age. When does the book value equal 8,000? Okay, so the way we can do this is simply by saying, well, we know what the book value we want is. Okay, when can we sell it? So what we're going to do is we're going to say, well, that means that $8,000 has to be equal to the negative $4,000, or our function that we came up with. Okay, we're going to start solving, so I can simply subtract 28,000. Subtract 28,000 from each side, we get negative 20,000 is equal to negative 4,000 x, divide by negative 4,000 on both sides, and we get an age of 5 years. So again, just kind of looking at what this looks like on our graph at 5 years old, the company is putting a value of only $8,000 on it. Okay? And we can also say from this that at 7 years old, it's worthless. Okay? All right, so building linear functions aren't too bad. All right, one more example. It says, the quantity supplied of a good is the amount of product that the company is willing to make for sale at a given price. The quantity demanded, so these are some definitions that you may want to highlight. So quantity supplied is the amount a company is willing to pay supply for a sale, and the quantity demanded is the amount that a customer is willing to buy. Okay, and we can so I'm going to give you guys a couple of equations. So these are not necessarily the equations that we're going to use every single time, but this is specifically for this example. Suppose the quantity supplied, S, and the quantity demanded D of cell phones each month are given by the following functions. Okay, so we're going to be using these two functions to figure out these next few parts, where P is the price in dollars of the cell phone. The equilibrium price of a product, so again, this is another definition that we're going to go into. The equilibrium price of a product is defined where the quantity supplied is equal to the quantity demanded. And we can simplify that by this here. Okay, so the supply at a given price is equal to the demand at a given price. We want to find the equilibrium price of the cell phones. What is the equilibrium quantity? The demand, which is just the amount demanded at that price. Okay, so this is going to take just a little bit of work. Okay, so finding the equilibrium price, so part A, is simply going to be setting the supply equal to the demand. Okay, so when we're solving this, it's simply going to be, well, we know that S of P is 60, P minus 900, and the demand at the price is negative 15, P plus 2,850. Okay, now we're going to start solving for P, so I'm going to add 15P to both sides, so that's 75P. I'll go ahead and add 900 to the other side as well. So we have, that'll be 3750. Okay, then we're going to divide by 75, and we get that P is equal to $50. Okay, so if you set your cell phones, and this is definitely a problem from around 2005, but if you set your cell phones at $50, your supply will be equal to the demand. Okay, so you should expect that you can sell as many as you put out. Okay, so that is the equilibrium price. The next thing it's asking for is what is the equilibrium quantity? Okay, so the amount demanded at the equilibrium price. Okay, so the way we're going to do this is simply by plugging this value that we just found back into our function. So it doesn't matter which one, right? So they're equal to each other at this point. So we can just plug it in. So the demand, so the amount demanded times of 50 is equal to negative 15 times 50 plus 2,850. Okay, working this out in your calculator, you get a quantity demanded of exactly 2,100 cell phones. Okay, so at $50, you can expect to sell 2,100 cell phones. Okay, we can do the same thing. So now it says determine the prices for the quantity for where the quantity supplied is greater than the quantity demanded. Okay, so we're going to use the same. So let's see if I can make this smaller. Nope. We're going to use the same format in order to solve this one. Okay, so I'm going to move. All right, give me just a sec, guys. Oh, yeah, I can't make it smaller. All right, so I'm going to make this smaller so we can actually write in here. All right, so we're looking for where the quantity supplied is greater than the quantity demanded. I'll do this in green so we can kind of see the difference, see what we're doing. So part B, we want supply to be greater than demand. Okay, we know that supply is 60P minus 900, and demand is negative 15P plus 2850. Okay, again, solving in the same process that we solved down here. We do end up with P being, let's see, I'll just work it out. So 75P is greater than 3750. So P being greater than So our price being more than $50 tells us that our supply is greater than our demand. Okay, so if we set the price greater than $50, our supply is bigger than our demand. All right, so if I'm to graph this, okay, I'm going to graph both of these equations separately. Okay, so I'll do the demand equation first. The demand, we know, starts up here around $2,850, and the demand function, sorry, the supply function actually starts down here at negative $900. Okay, so we're looking for the intersection. Okay, so down here we're not using the graph, but it starts becoming a solid line right up here, and then we're going to have our supply function right here. Okay, so this is demand, this is supply. Okay, and it asks us to label the equilibrium point. So all I'm going to do here is simply, now that I know where these kind of graphs kind of go, I'm simply going to label our supply point. So this would be, or our equilibrium. So we have $50 will sell us 2,100 cell phones. Okay, so if we're kind of looking at this, if I'm looking at the supply greater than demand, what I'm looking at is where the supply line, so this line, is above my demand line. So that would be this interval here. Okay, so this is where my supply is greater than my demand. Okay, when that happens, notice, so remember that the x value is the x-axis is actually our p-axis. This is our, the other axis is the quantity axis, so how much you supply. Okay, so when your supply is greater than your demand, you have to when your supply is greater than your demand, you have to actually lower the price in order to, so you have to lower the price in order to sell all your cell phones. However, if we're looking over here, where the demand is greater than your supply, you can actually start raising your price. Okay, so the equilibrium point is where you're really looking for, but this is going to maximize your profits. But if you have a small demand, your price needs to be big. If you have a really big supply and not as much demand, you're going to have a lower price.